Hey everyone, welcome back. So, let's just dive right into it. Today we're tackling a foundational concept in object-oriented programming. And honestly, this is absolutely critical for your upcoming Week 6 and Week 7 exams and assignments. We're going to master object relationships, specifically zeroing in on inheritance and C++ constructors. If you've ever felt a little, overwhelmed by how classes actually interact with one another under the hood, well, grab your notepad. Because by the end of this explainer, you're going to see exactly how these abstract ideas seamlessly translate right down into the compiler's memory.
Let's start with a quick logic puzzle, right? Think about the real world for a second. If a Ferrari is a car, and a car has a driver, how do we write code that actually understands that specific relationship? See, object-oriented programming isn't just about throwing functions and variables into a file. It's really about mapping these physical, real-world relationships directly into computer memory. We want our code to reflect reality, because that's what makes our software highly reusable and, honestly, incredibly easy to maintain down the line.
Here's our roadmap for today's explainer. First, we'll look at the types of object relationships. Then, inheritance, the is-a relationship. Third, we'll dive into coding inheritance in C++. Fourth, we'll look at constructor call order. Fifth, aggregation versus composition. And finally, a final review with some golden rules.
All right, kicking things off with Section 1, Types of Object Relationships.
So out in the real world, and definitely in our code, classes rarely exist in total isolation. They gotta interact, and they do so in very specific, categorized ways. According to our source material, OOP generally supports 4 main types of relationships, which we can basically group into 3 core buckets. First up, we've got the is-a relationship, and that's implemented through inheritance. Second, there's the part-of relationship, handled by composition. And third, the has-a relationship, which covers aggregation and association. Figuring out whether an object logically is a thing or has a thing, that is the absolute critical first step you have to take before you write a single line of code.
Moving right along to Section 2, Inheritance, or the is-at relationship.
Okay, zooming in on the most famous OOP relationship of them all. But before we look at any actual code, let's lock down the vocabulary you're going to need for your assignments. The technique of deriving a new class from an old one, that's called inheritance. The old class, the one whose properties are being inherited, is called the superclass or the base class. On the flip side, the new class, the one that inherits those properties and usually adds a bunch of its own, is called the subclass or derived class. So the really crucial takeaway here is that the subclass contains literally all the features of its parent plus its own unique extensions.
Let's follow the data flow for a second to see what this looks like. Imagine we have a base class called animal, with your standard functions like eat and sleep. Right below it, we have a derived class called dog. Now, because a dog literally is an animal, it just naturally inherits those eat and sleep methods from the parent. We don't have to rewrite that code. The dog class only needs to define its own unique function, like bark. Talk about a game changer for code reusability and maintainability, right?
Now check out how the hidden architecture inside the computer's memory is actually structured. Imagine a student-derived class inheriting from a faculty-based class. Even though you might only type out the brand new properties when you're coding up the student class, in memory, the student object logically contains all the data members and methods of that faculty parent class right alongside its own. They are fundamentally fused together into one package.
All right, Section 3, Coding Inheritance in C++.
Okay, so we've got the theory down. Let's see how C++ syntax actually builds this is-a relationship in practice. Honestly, to implement inheritance in C++, the syntax is incredibly concise. When you define your derived class, you literally just write the class name, followed by a colon, an access modifier like public, and then the name of the base class. It's that simple. So typing class child followed by public parent visually and logically links the child to the parent right at the moment of creation.
Let's walk through the exact flow of data here, based on the lecture examples. First, you define the base class, let's say a parent class, with an integer variable called IDP. Next up, you define the child class using that exact same colon syntax we just talked about, and maybe you give it its own integer variable, IDC. Now here is where the magic happens. When you go into your main function and create a single instance of the child class, let's call it object1, that one single object has access to everything. You can set object1.idc equal to 7, and you can also set object1.idp equal to 91. Creating an instance of the subclass just hands you the keys to the entire inherited chain of variables.
Next up, Section 4, Constructor Call Order.
You're going to want to pay super close attention to this next sequence, because this hidden compiler behavior, it is highly, highly tested by professors. Whenever you create an object of a derived class, a very specific sequence of events kicks off behind the scenes. Think about it. Before the child can be built, the parent has to exist, right? Therefore, step 1 is that the base class's default constructor is invoked automatically. Then, once the parent is totally fully constructed, step 2 triggers, and the derived class's default constructor is invoked. It's exactly like building a house. The machine has to pour the foundation, the parent, before it can possibly build the second floor, the child.
Now, here is an extremely common pitfall, one that trips up students on assignments all the time. By default, the compiler only knows how to automatically call the default constructor of the base class. But what if your parent class has a parameterized constructor? Like, what if it absolutely needs an integer to be built properly? Well, the compiler isn't going to guess this for you. To use a parameterized base constructor, you must explicitly mention it in the derived class's constructor definition. You do this by putting a colon right after the derived constructor's parameters and explicitly calling the base constructor. For example, derived int j colon base j. This explicitly passes the data straight up the chain to initialize the parent. Do not forget this syntax. It's a huge deal.
Moving into section 5, aggregation versus composition.
So let's see how this rounds out our total understanding of OOP. Because let's face it, not everything is a relationship. Sometimes objects just contain other objects. Comparing them side by side, both aggregation and composition involve objects holding other objects, but the strength of that bond is totally different. Look at the real-life examples here. Aggregation has a relationship, and it's considered weak. For instance, a car has a driver, but the parent and child are completely independent. If the car gets totaled, the driver still exists and goes about their life, right? Composition, on the other hand, is a part of relationship, and it is incredibly strong. A car is composed of wheels. If you destroy the car, you are fundamentally destroying the conceptual instance of its wheels. In composition, the parent controls the lifetime of the child object entirely.
So, you might be wondering, how do we actually code a has-our relationship without using inheritance? We'll take a look at this employee class snippet. Look closely inside the private members. Notice that line that says address star address? The employee class isn't inheriting from address with a colon. Not at all. Instead, it literally contains a pointer to an address object right there as one of its variables. This is exactly what a has-a relationship looks like in C++. The employee simply holds a reference to another, entirely separate class.
And finally, Section 6, Final Review and Golden Rules.
Okay, we've covered a tremendous amount of ground today, going all the way from abstract logical relationships down to literal memory pointers and compiler execution orders. So let's bring all these concepts together for a rapid-fire recap. Seriously, consider this your ultimate study guide, your OOP cheat sheet. Rule number 1, use inheritance when you have a clear ISA relationship to gain code reusability. Rule 2, if an object simply contains another object, like a has-a or part of relationship, use composition or aggregation by throwing some object pointers in there as class variables. Rule 3, always remember that hidden compiler behavior. Constructors fire top-down. The base class foundation is always built before the derived class. And finally, Rule 4, if your base class needs parameters to be constructed, you have got to explicitly call that parameterized constructor from the derived class. Honestly, memorizing these golden rules alone will keep your code bug-free and pretty much guarantee success on your assessments.
I'm going to leave you with this final provocative prompt straight from the lecture material. When exactly should you use an ISA relationship versus a has-a relationship? I'll challenge you right now. Look away from the screen, take a look around the room you're in, and try to map the objects around you. Can you spot a real-world example of inheritance? What about a real-world example of composition? Testing yourself conceptually like this is hands down the best way to lock in this knowledge. Anyway, thank you so much for learning with us on this explainer, and hey, best of luck mapping out your code.